You think you know what happens when you stretch a rubber band. You pull it, it resists. You feel that tension building in your fingers. And when you let go, snap, it flies back. Simple, obvious, elastic force. The rubber wants to return to its original shape. That's what you think is happening. But let me ask you something. Why does it want to return? What is that wanting? Where does that pull come from? You'll probably say something about molecules being stretched. The rubber gets longer, the molecules get pulled apart, and they want to come back together. Like a spring, like a coiled piece of metal that you've compressed or extended. Release it, and the stored energy pushes it back. That sounds reasonable. That sounds like physics. And it's almost completely wrong. Here's the thing that's going to break your understanding of everyday objects. Rubber bands don't work like springs. The force you feel isn't stored energy fighting to escape. It's something else entirely. Something stranger. Something that connects a child's toy to the deepest principles of thermodynamics, to the same laws that make time flow in one direction, that make your coffee cool down instead of heat up, that make the universe itself evolve from order to chaos. The rubber band snapping back is entropy. And once you see what that really means, you'll realize that what you call intuition about the physical world is mostly a collection of comfortable lies your brain tells you to get through the day. Let me show you. Pick up a rubber band, any rubber band. Hold it between your fingers and stretch it slowly. Feel that resistance. Now, here's something almost nobody notices. Touch the stretched rubber band to your lip. Your lip is very sensitive to temperature. What do you feel? It's warm. The rubber band got warmer when you stretched it. Not by much, but it's there. Measurable. Real. Now let it snap back. Touch it to your lip again. It cooled down. That's strange. That's very strange. And if you think about it with your normal intuition about elasticity, it makes no sense at all. When you stretch a metal spring, it doesn't heat up. When you compress a metal spring, it doesn't cool down. The energy goes into the bonds between atoms, sits there as potential energy, and comes back out when you release it. The temperature stays the same, but rubber heats up when stretched and cools down when released. Something fundamentally different is happening, and until you understand what that difference is, you don't understand rubber bands at all. Let's start with what rubber actually is. Rubber is made of very long molecules, polymers, chains of atoms linked together, thousands of units long. These chains are flexible. They can bend and twist and coil in countless different ways. At room temperature, they're constantly jiggling. Everything is jiggling. Every atom in the universe is in constant thermal motion. The hotter something is, the more violent the jiggling. The colder, the more sluggish. These long polymer chains at rest are tangled. They're coiled up on themselves in random configurations, not because they're trying to be tangled, not because tangling is some preferred state, but because there are astronomically more ways to be tangled than to be straight. Think about that for a second. Take a piece of string, throw it on the floor. What shape does it land in? A tangled mess. Try it again. Another tangled mess, different from the first, but still tangled. Try it 1,000 times, 1,000,000 times. You will almost never see that string land in a perfectly straight line. Why? Not because the string hates being straight, not because some force is fighting against straightness, but because there's only one way to be perfectly straight. There are billions of ways to be tangled. Probability, pure probability. If you randomly sample all possible configurations of that string, almost all of them are tangled. Straight configuration is there in the space of possibilities, but it's 1 in a billion billion. You'd have to wait longer than the age of the universe to see it happen by chance. This is the key to understanding rubber. The polymer chains in rubber are constantly being pushed around by thermal motion. They're jiggling, bumping, randomly reconfiguring. And because random motion explores all possibilities, and almost all possibilities are tangled, the chains stay tangled. Now you stretch the rubber band. What happens? You're forcing those tangled chains to straighten out. You're taking them from a tangled configuration to an elongated one. You're reducing the number of possible arrangements they can have. A tangled chain can be tangled in countless ways, but a straight chain can only be straight in one way. You've reduced the options. You've reduced the randomness. You've reduced what physicists call the entropy. And here's the profound thing. When you reduce entropy mechanically, when you force a system into a less probable state, energy has to go somewhere. The thermal motion of the molecules doesn't disappear. It gets converted. Some of that random jiggling becomes organized motion, which shows up as heat. That's why the rubber band gets warm when you stretch it. You haven't stored energy in stretched bonds. You've reduced entropy and released heat in the process. Now let it go. The chains are no longer being held straight. They're free to explore all configurations again. And what configuration will they find? The tangled one. Not because tangling is preferred, not because some force pulls them into tangles, but because random jiggling thermal motion naturally explores all possibilities. And almost all possibilities are tangled. The chains retangle themselves. Entropy increases. And as entropy increases, the system absorbs heat from the surroundings. The rubber band cools down. This is the secret. This is what your intuition completely misses. A metal spring stores energy in stretched bonds. Release it, and the energy comes back as kinetic energy of the spring. It's an energy game. A rubber band stores order. It stores low entropy. Release it, and entropy increases. The random thermal motion of molecules pushes the chains back into tangles. It's an entropy game. The force you feel when you stretch a rubber band isn't from molecules pulling on each other. It's from molecules jiggling randomly in a way that statistically favors retangling. It's thermal motion doing work through probability. Let me make this even more concrete. Imagine you have a room full of people walking randomly. They're blindfolded, taking steps in random directions. Now you line them all up against one wall. You've created order. Low entropy. They're all in one place. Remove the constraint. Let them walk randomly again. What happens? They spread out. They fill the room. Not because they want to spread out, not because some force pushes them apart, but because random walking explores all positions, and there are more positions scattered around the room than lined up against the wall. The spreading is just probability manifesting over time. Now imagine the room has soft walls. When the people bump into the walls flex. The random motion of the people bumping into the walls pushes the walls outward. That's what happens in a rubber band. The polymer chains are the people. The stretched rubber is the lined-up configuration. The random thermal jiggling is the random walking. When you try to hold the chain straight, they bump against that constraint. Their random motion creates a statistical pressure to retangle. That statistical pressure is the force you feel. It's not a force in the usual sense. It's not electrons repelling electrons or atoms tugging on atoms. It's pure statistics. It's probability pushing. This should disturb you. You thought force was something fundamental, something real, push and pull, attraction and repulsion, but here's a force that emerges entirely from randomness and probability. The rubber band snaps back because random is easier than ordered. That's all. That's the entire explanation. Here's a test. Here's how you know this is true and not just theoretical hand-waving. Heat up a rubber band under tension. Keep it stretched, but heat it. What happens? If rubber worked like a metal spring, heating would make it expand. Metal springs get longer when heated. The atoms vibrate more. They need more space. The material expands. But rubber under tension contracts when heated. It gets shorter. It pulls harder. Why? Because heating increases the thermal jiggling. More jiggling means more aggressive exploration of configurations. And since tangled configurations vastly outnumber straight ones, more aggressive jiggling means more aggressive retangling. The statistical pressure increases. The force increases. The rubber pulls harder and contracts. This is backwards from everything you'd expect. This is the opposite of how normal materials behave, and it proves that rubber elasticity is entropic, not energetic. The force isn't from stretched bonds. The force is from thermal chaos. Now think about what this means for your intuition. You stretch a rubber band. You feel resistance. You think the rubber is fighting me. The molecules don't want to be pulled apart. But the molecules don't want anything. They're just jiggling. They're bouncing around randomly at thermal velocities. When you straighten them out, their random motion happens to create a statistical push against whatever is holding them straight. When you release them, their random motion happens to take them back to tangled states. There's no wanting. There's no preference. There's just probability playing out over billions of molecules. And this isn't just about rubber bands. This principle is everywhere. Why does heat flow from hot to cold? Entropy. Why does gas expand to fill a container? Entropy. Why does ice melt at room temperature? Entropy. Why do mixtures mix? Entropy. Why can't you unscramble an egg? Entropy. The same principle that makes a rubber band snap back is the principle that makes time seem to have a direction. Past is different from future because entropy was lower in the past and higher in the future. We remember yesterday because memory formation increases entropy. We can't remember tomorrow because that would require entropy to decrease. The rubber band connects to everything. Let me push this further. You might think, okay, so rubber is weird, rubber is special, but normal solids, normal springs, those work differently. And you'd be right, metal springs really do store energy in stretched atomic bonds. The elasticity of steel is energetic, not entropic. But here's the thing. The feeling of force, the sensation of resistance, your intuition doesn't distinguish between entropic and energetic forces. Your fingers can't tell the difference. When you stretch a rubber band and when you compress a metal spring, the resistance feels similar. Force is force to your nervous system. And that means your intuition is fundamentally unreliable when it comes to understanding what's actually happening at the atomic level. You feel force and you assume something is pulling or pushing. But sometimes what you're feeling is pure statistics. Sometimes what you're feeling is probability manifesting as mechanical resistance. This is why physics is hard. This is why you can't just think your way to the right answer by imagining little balls connected by springs. The universe is weirder than that. The universe is weirder than your intuition, built for throwing rocks and picking fruit, can possibly encompass. Here's another mind-bending aspect of this. I said that rubber band elasticity is entropic. The force comes from thermal, motion, and probability. But think about what that means for energy. When you stretch a metal spring and release it, the stored potential energy becomes kinetic energy of the spring, conservation of energy. When you stretch a rubber band and release it, there's no stored potential energy. The energy went into heat when you stretched it. The rubber warmed up, remember, that heat dissipated into the environment. So where does the kinetic energy come from when the rubber band snaps back? From the environment, from heat. When the rubber band contracts, it absorbs heat from the surroundings. It cools down. That absorbed heat is what powers the snap. The thermal energy of the surrounding air becomes kinetic energy of the rubber band. This is remarkable. This is a heat engine operating at room temperature with no moving parts except the rubber itself. And it gets more remarkable. In principle, with perfectly idealized rubber, this process is reversible. You could stretch and release the rubber over and over, and it would act as a perfect heat engine, converting thermal energy to mechanical work with no fundamental losses. Of course, real rubber isn't perfect. There are other energy losses, friction-like effects within the material. But the underlying entropic elasticity is thermodynamically beautiful. It's nature using probability as a power source. Now let's go even deeper. I've been talking about polymer chains retangling because there are more tangled configurations than straight ones. But how many more? What are the actual numbers? This is where physics gets truly mind-boggling. A single polymer chain in rubber might have thousands of units. Each unit can be in various orientations. When you calculate the number of possible configurations, you're dealing with numbers like 10 to the power of something enormous. More configurations than there are atoms in the observable universe. And the straight configurations? Those represent an incomprehensibly tiny fraction. One specific arrangement out of more possibilities than you could write down if you used every atom in existence as a digit. The probability that a free polymer chain spontaneously straightens is so small that it effectively never happens. Not in the lifetime of the universe, not in the lifetime of a billion universes. This isn't approximation. This isn't hand-waving. This is the hard mathematics of combinatorics and statistical mechanics. The numbers are real. The probabilities are calculated. And those probabilities give rise to forces, real forces, measurable forces, forces you feel when you stretch a rubber band. Probability becomes physics. Counting configurations becomes predicting mechanical behavior. This is one of the deepest insights in all of science. The microscopic world of atoms jiggling randomly gives rise to the macroscopic world of forces and pressures and engines. The bridge between them is statistics. The bridge is probability. When you understand this, you understand something profound about the universe. The laws of thermodynamics aren't just rules about heat and work. They're statements about probability. They're recognitions that systems with more possible configurations are more likely than systems with fewer possible configurations. And because more likely in a world of astronomical numbers means essentially certain, we get definite laws. Heat flows from hot to cold. Entropy increases. Time has a direction. Rubber bands snap back, not because the universe has preferences, not because some cosmic rule book says so, but because some things are probable and some things are fantastically improbable, and we only ever see the probable things happen. Let's come back to that simple question I started with. Why does the rubber band want to return to its original shape? Now you see why the question is broken. The rubber band doesn't want anything. The word want is a trap. It's a linguistic trick that makes you think there's some inner drive, some preference, some purpose. There's no purpose. There's just atoms jiggling. The straight configuration is one arrangement among billions of billions. The tangled configurations are everything else. Random jiggling explores all arrangements. Almost all arrangements are tangled. Therefore, the chains end up tangled. Therefore, the rubber band contracts. The wanting is an illusion created by astronomical statistics. And here's the really uncomfortable part. The same is true for every time you use the word want about physical systems. Water doesn't want to flow downhill. It just does, because gravity pulls it. And there are more ways to be at the bottom than at the top. Heat doesn't want to spread out. It just does because random jiggling explores all positions and spread out configurations vastly outnumber concentrated ones. Even when we talk about atoms wanting to bond, we're using misleading language. Atoms don't want anything. But bonded configurations have lower energy. And systems naturally find lower energy states because higher energy states are unstable. The wanting is just shorthand for probability and energy gradients. Physics doesn't have purposes. Physics doesn't have desires. Physics is just stuff happening according to rules. And sometimes those rules are just probability manifesting at scale. This should change how you see everything. The next time you stretch a rubber band, remember what you're really doing. You're forcing order on chaos. You're taking tangled polymer chains and straightening them. You're fighting against the statistical pressure of thermal motion. And when you release it, you're not releasing stored energy. You're releasing probability. You're letting randomness do what randomness does. You're watching entropy increase. The snap of a rubber band is the universe shuffling back toward disorder, the same drive that makes stars burn out. The same principle that makes heat flow. The same inexorable tendency that shapes the fate of everything. In your hand, with a child's toy. Here's the beautiful thing, though. Understanding this doesn't make the rubber band less useful. It doesn't make elasticity less real. The force is still there. The snap is still there. You can still use rubber bands to hold things together and launch paper airplanes and whatever else you use them for. But now you know what's really happening. You know that the simple sensation of elastic force is actually a window into the deepest structure of physical law. You know that probability can become force. You know that randomness can do work. And you know that your intuitions, those comfortable feelings about how things should behave, are just approximations. Useful approximations for getting through daily life. But approximations nonetheless. The universe is stranger than it feels. The universe operates on principles that don't match the low-speed, room-temperature, medium-sized object reality your brain evolved to navigate. Rubber bands snap back because of entropy, because thermal jiggling explores all configurations, because tangled is more probable than straight, not because they want to, not because they're trying to return, not because some inner drive compels them, just probability, just physics, just the way the universe happens to be. And isn't it better to know? Isn't it better to see through the comfortable illusion to the strange, beautiful, counterintuitive machinery beneath? That's what physics offers. Not comfort, not familiarity, truth. The rubber band in your hand is a direct connection to the second law of thermodynamics. It's a demonstration of entropic force. It's proof that what you feel isn't always what's happening. And now when someone asks you why rubber bands snap back, you can tell them the real answer. It's not about molecules wanting to return. It's about probability. It's about thermal motion. It's about the universe's relentless shuffling toward disorder. It's about entropy. And it's about the humbling fact that even the simplest objects in your kitchen drawer are operating on principles that took centuries of human genius to uncover, principles that connect a child's toy to the arrow of time itself. That's what's between your fingers when you stretch a rubber band. That's what snaps back. Not stored energy, not molecular tension. Just the universe being the universe, random and beautiful and utterly indifferent to what you think should be happening.